If you ask me, I would say this question should be worth 7 to 8 marks. Because there's a lot of things that we do here. It takes time, and also it's not an obvious question to do. You need to do a little bit of thinking before you can do this question. So sometimes examiners will be unfair in that sense that they'll give you long questions that take more time for low marks. But remember, the strategy here is not to complain, but it actually is to execute. So the advice that I will give you for you to be able to execute is that practice as many exam questions as you can, because that will allow you to save time when you get to the exam. You will be familiar with these questions when you do them. You'll already know what to do. You'll spend less time thinking, and also you'll flow with the mathematics because already you have practiced. That's the only chance you have in terms of acing these questions. I am truly excited to share with you the memo of question 3 of the November 2015 final examination. As usual, before we can begin this question, I'm going to write my academic constitution that says I can. This is a problem-solving strategy that will be following the step-by-step processes that will be following when we solve this problem. The I stands for interpretation, the C stands for classification, the A stands for answering the problem, and N, we navigate our answer. To interpret this problem, I'll begin by reading the question, which says ball A is projected vertically upwards at a velocity of 16 meters per second from the ground. Ignore the effects of air resistance, and very important, use the ground as the reference point. Perhaps the first thing that I would like to do in doing this question 3 is really to choose direction. So I'll say take upwards as positive. This would mean that any vector that goes upwards would be positive. Now we have a diagram in this problem, so I'll use the diagram to interpret the problem. So we have this ball that is thrown vertically upwards at 16 meters per second, and it will go up like that until it reaches the maximum height or position. Then it will then change direction and go downwards to come back to the ground. And we are saying here that the ground is actually the reference point. That means it is the origin. It is where we start to measure our height or positions. For instance, we know that from here to the top of this building, it is 30 meters per second. 30 meters because we're actually measuring it from 0. So we measure from here going upwards. That's what the reference frame would mean, is where we start to do our measurements. Now, this ball will actually have a trajectory that is given by something like this, and it will then come back to this point. This initial velocity here, I'm going to call it the initial velocity of ball A, and is positive because we chose up as positive. Because in our question they said that we should ignore the effects of air resistance, it means that there are no any other forces except the gravitational force. And that would mean that this ball is actually accelerating with a constant acceleration, which is given by negative 9.8 meters per second squared. This is the acceleration due to gravity. It always points vertically downwards. That's why here I'm saying it's a negative, because we choose up as positive. Now, I think this should be enough interpretation for this specific part of the problem. What I will then look at or pay attention to now would be the classification of this problem. I will classify this problem as a problem that requires the knowledge of vertical projectile motion. It is possible to also classify this problem as one that requires the knowledge of work, energy, and power. Or you can also solve this problem using impulse and momentum. Any of those methods will work. For now, I will stick with using the vertical projectile motion knowledge, meaning the equations of vertical projectile motion and any theory that we know from that side, because we're just at the beginning of the year. We haven't done other topics. You can also explore the impulse momentum theorem because already we have done that section. Now, after classifying this problem, really what I'm going to do, I'm now here at A, I'm going to answer the questions. Question 3.1 says, calculate the time taken by ball A to return to the ground. So what we want here is that we want the time it takes for the ball to go up and come back to the ground here. So that is to say, we're actually looking at 3.1, we're actually looking at calculating the total time of object A or the ball A, because this will be the total time that it takes for this ball to be in motion. I am going to use this equation of motion here that says change in y is equals to the initial velocity of ball A times change in time of A, total time that it takes, times half the acceleration due to gravity, times change in time that it takes for the ball to go up and down, the total time. Now, you would notice that there are other equations that you can use to calculate this time, the equations of motion, but I'm specifically going for this one. You can choose any one that you like. In other questions, I've used other equations just to give you different methods of doing these problems. So in this question, I'm choosing this equation. I encourage you to also practice other methods, just so you explore which one becomes easier for you, and also to, stretch that muscle of vertical projectile motion in preparation for the exams. I want to talk a little bit about the displacement here. We know that the projectile starts at the initial position of A at the position of 0 meters. Because it is at the ground and we said the ground is 0, so the initial position, YA initial of ball A would be 0. And this ball returns to the ground. That means the final position, YA final, is also 0 meters. So this ball really starts at the position of 0 and comes back at the position of 0. The change in position, the displacement, which is change in y, is given by change in y final minus change in y initial. But here I'm saying of ball A because we're looking at ball A. And we can see that the final position of this ball is 0 and the initial position is also 0. So we're going to have 0 minus 0, and this means that our displacement, change in y, is actually 0 meters. And actually this makes sense because what we're saying here is that we're saying the ball here is moved up and came down to where it started. But when you look at it, it was not displaced. It is still exactly at the same position where it started. There's no displacement. So that is to say here our displacement is 0 because there's no displacement. And we know that our initial velocity is 16. Then we're going to multiply that by the change in t total plus. Here we have 1 over 2. Then we have negative 9.8. Remember, it's negative because it's going down. Then we're multiplying here by 80 squared. Now, at this stage, we have looked at this type of equation before. We know that it's a parabola, right? it has a common factor of change in t. We can take that out as a common factor, so that we have now here the change in TA total. Here I'm going to have a 16, and when I multiply these two, they should give me negative 4.9, and we have the change in t 80 squared. Now if I multiply this back, I'm going to get that. If I multiply this back, I'm going to get the t squared, and this is just the 4.9 is just the same as half of 9.8. Now at this stage, this question becomes really boring, because this is an algebraic equation where we are saying that two products are equals to 0, and that will mean either one of these products is equals to 0. Now this is a typical solve for x question in mathematics. So we're going to say, so I'm going to do this here. I'm going to say the change in TA is equals to 0, right? This is equals to 0, or this is equals to 0. So here we're going to have a 16 minus 4.9 change in t. Remember, we don't have the square anymore here, just so we fix that. We don't have the square anymore there. So this will be a TAT squared is equals to 0, right? We're saying either this is equals to 0 or this is equals to 0. Now you would see that I have tactically removed the t here, but here I've kept the t, because I realized that the time here is 0, and you know, when t is 0 is at the beginning of the motion, it cannot be the total time. So that means this is the initial time of the projectile, is the time when the projectile was projected, it was launched vertically upwards. And here we should get the total time. It should give us the time when it comes back, when it's here, how long it has taken to go up and down. Now to solve this part of the problem is really simple, because we are just going to use a calculator where, okay, I keep on writing this square, I don't know why. So here we don't have a square anymore, where we are really going to take the 16 to that side, so that we have this side the negative 16, because it's going to be negative when it comes to this side, and we are going to divide by 4.9 and negative 4.9 also this side. The 4.9 and the 4.9 will cancel, then I'm only left with the changing TA total, and this side I'm just going to punch that on a calculator. So on my calculator, I'm going to have negative 16 divided by negative 4.9, and that gives me the total time of 3.27 seconds. Now this is our answer. This is the total time that we want to calculate, and this is not what we're looking for. This is the time at the start of the motion, so we're required to calculate this one here. Now that I've answered this question, we can navigate the answer. To navigate the answer, you just check if there's errors and if you've calculated the correct quantity. Of course, here, you know, I've been fixing also my labeling to say this is total time, this is initial time. So I've made sure that I calculate the total time, so the symbol is written correctly. The number and the SI units are there. And also the other thing to with time that is interesting is that our time, when it comes out to be positive, it tells us that we are at least in the right direction, because time cannot be measured in negative numbers. It is not a vector, it is not attached to a direction. And my number looks really good. It's not so much of a big number, it's about 3 seconds if you like. So it could make sense that a projectile that is projected at 16 meters per second going up and down, it can take 3 seconds, because this is fairly fast if you look at it from that perspective. That is the last rule that we apply of navigation to our problems. We don't move to the next question without checking our answer. that will allow us to score the 4 marks when they mark us, because they will mark here using the correct formula. The fact that you put 0 here, very important. You know what I did here, even though you may not necessarily write this step down, but it's important. They give you a mark for being able to recognize this displacement to be 0. Then they give you a mark for the correct substitution in everything here. Then the other mark will really come from choosing this answer, writing the correct one and not necessarily taking this one here. Now we can move to the next question that says to us that sketch a velocity versus time graph for ball A. Now to sketch this graph is relatively easy at this stage because we have went through the whole playlist or lessons in how to sketch these graphs. So the first thing that I'm going to do is to write my title to say I'm drawing a velocity versus time graph. Very important in science to label your diagrams, your tables, and also graphs. Now we know that to draw a velocity versus time graph, we really use the equation of a straight line that says final velocity is equals to the acceleration times time plus the initial velocity. This is just the equation of motion rearranged. And it basically says y is equals to mx plus c. Now you would see that the m here, which is the gradient of the straight line, is the acceleration due to gravity. The x here is the time, so it is the x-axis. Time will be drawn in the x-axis. And the c here, which is the y-intercept, is our initial velocity. So to draw this graph, we basically need two things. We need to know the gradient of our line, because this thing is a straight line. And we also need to know where it cuts our y-axis. Then we are done. All other numbers we'll put in there because we have calculated them in the previous questions. I'm going to do exactly that by drawing my y-axis here and also drawing my x-axis here. And we are saying that the x-axis is defined by time because it is, the independent variable. And my velocity, you can write this as v measured in meters per second, or you can write it in weights to say velocity in meters per second is the same thing. And we know that on the Cartesian plane, this is the origin, this is 0, meaning our x-axis here is 0, and also our y-axis here is 0, meaning both the time and the velocity are 0 at this point. It is at the start point, is where the motion begins, where the ball has been thrown. It is the ground, in other words. Now, to draw this graph, I will then come and say that my y-intercept, the c, here, the y-intercept, the c, is actually given by the velocity of 16 meters per second, and is a positive number because we chose up as positive. Remember, this projectile is actually going upwards, and we chose that direction as positive. We said the 16 is positive. That means the graph should intercept a positive number here of 16. Is a point here. When the time is 0, we get a point 16 there, which is the initial velocity. The other thing that I'm going to really look at would be the gradient, which is g here. Our gradient is equal to negative 9.8 meters per second squared, and we know that a line that has a negative gradient actually goes downhill. Is a line that should go like that. Is a line that goes downhill, and actually this line will begin, it will intersect the y-axis here at 16. So here at 16, so that means my graph should start here and go down like that. And I'm going to simply just draw that. We are having a line that goes like that here. So this is our line. So here we got the shape right, we got the y-intercept, which is the initial velocity, right? Then I can put all the other information that I have. When we studied our vertical projectile motion graphs, we said this part of the graph represents upward motion. Right, so it means now at this point here is when we reach the maximum height, and you can see that the velocity is actually getting smaller and smaller and smaller until a point where it is 0. So it means at this time we get a velocity of 0, and that should actually be here at the maximum height, because we know that the velocity here is 0 meters per second. Now when the velocity is 0 meters per second, our time would be the maximum time here, right? But we don't have that time. We actually have the total time. We have the time that it takes the projectile to actually come back down. So that is to say that we know that from here going down is the part where the projectile is actually coming down like that, is that part of the motion. Now that means from here to here is going to the maximum height, and going down here should give us the total time. So this means here the total time would be 3.27 seconds. So the time it takes to go up and down is that 3.27. Now because projectile motion is symmetrical, meaning the time it takes to go up is the same as the time it takes to go down, we are going to take half of this total time to then get the time here. Remember, usually we were multiplying the time we get here by 2 to get this one. So now we do the reverse. We actually divide that by 2. So that means I take this answer, which is still on the calculator, and then I divide by 2. Okay. This is 3.27 divided by 2. So this means here I'm going to have a 1.64 seconds. And we said the velocity will be 0 there. Now the velocity of this, when it actually comes back to the ground, will actually be defined here to be a negative 16 meters per second. Remember, when the projectile gets to this point, when it returns to this point, it will have the same velocity it had when it went up of 16 meters per second, but in the opposite direction, because vertical projectile motion is symmetrical. Remember speed symmetry. The speed of going down is the same as the speed of coming down. The speed of going up is the same as the speed of coming down. That's why here the speed that it went up with will be the same as the speed that it comes down with. So that's basically how you will then draw the graph and put all the information that you have. This specific type of question was marked out of 3 marks, and they required us to put specific things here. The initial velocity, that means they will mark that initial velocity here. They required us to put the time taken to reach the highest position of the ball, right? This is the time here. They will give you a mark for writing this time. It goes well with that velocity there, or speed, and also the time taken to reach the ground. So this is the time here. They'll also give you 1 mark for that. I'm not too sure why this was 3 marks, because usually they also give you a mark for the shape of the graph, getting the correct shape of this graph. Okay, I think in this case, how this will get marked actually is that 1 mark will go for these 2 times. They'll give you 1 mark for that, and the other mark will be for the shape, right? I don't know why they made it to be 3 marks. Usually it should be 4 or 5 marks, this type of a question. But at least be sure that you put all that information there to score that full mark of 3 marks. It's a very easy thing to do. Now we go to the other part of the question, which gives us more information. In other words, it gives us an opportunity to reinterpret the problem, because when they give us more information, they also would then give us change the situation as well, or give us additional data to interpret. They say here, 1 second after ball A is projected upwards. So after some time, 1 second, you see this ball will go up. Then after 1 second, I think when it's somewhere here, because if we look at our graph, actually, we can see that it takes 1.6 seconds to get to the maximum height. It means 1 second would be something somewhere here is before we get to the maximum height. So 1 second later, when we are here at 1 second, we actually start projecting the second ball. So when this ball is somewhere here, we then start throwing this one. Right, a second ball B is thrown vertically downwards. It's then now thrown vertical downwards at 9 meters per second from a balcony. So there's a balcony here above the ground. It's 30 meters above the ground. Now what that means here is that our initial velocity for ball B, let me write that correctly. We're saying our initial velocity for ball B will actually be equals to negative 9 meters per second. Is negative because we chose up as positive. Very, very important. Remember, we chose up as positive, so a vector that will go down will be negative. Right, so what I'm saying is that when ball A is somewhere here, just about to reach the maximum height, we throw this one vertically downwards with a velocity of 9 meters per second, which is at the height of 30 meters above the ground. And then they say refer to the diagram. So this is the diagram that we've been using already. Now question 3.3 says calculate how high above the ground ball A will be at the instant the two balls pass each other. Now, to answer this type of a question, what we are going to do is that, as I advised in the November 2014 question paper, to say when you want to answer this type of a question, look at each ball individually, pay attention to it individually. Don't try to solve them as if they are one thing. So by saying that, I'm going to focus my attention on this question 3.3 to say that I'm going to focus on ball A, where I will then come and say to define the displacement or the height of ball A, I'm going to say delta y is equals to VA initial times changing t plus 1 over 2 g times changing t squared. Now, on this equation, I'm going to build up the information that I have. I know that the initial velocity for ball A is 16, and here I have changing time, and this will give me 1 over 2 times negative 9.8, and I'm going to have changing t squared. Now, when I simplify this, I'll have an equation that says to us we have a 16 changing t, then here's going to be negative 4.9 times changing t squared. Now, this equation here is a function that represents the height or the displacement of ball A at any time. We know this when we discuss the graphs, the position versus time graphs, that is a parabola, this equation. It depends on the time. As we change the time here, the height will also change. So what I'm saying here is that when the time is 0, when we are here at the reference point, you would see that this is 0 here. The whole thing will be 0. Our displacement is 0 because we are at the reference point. When the time increases maybe to 1 second, that means we're going to put 1 second here. Then we are going to have the height that, or the displacement that the ball has moved to 1 second. It will give us that height. When it is at 2 seconds, we're going to get the height again. So as we change time, we define different heights that the ball will reach as it goes up and down. So that's what this equation represents. It represents the displacement as a function of time. It's basically a parabola that defines different heights. Now we are going to do the same thing for ball B, where we use exactly the same equation to say the height of ball B at any time will be given by the initial velocity of B times change in time of B plus 1 over 2g change in time of b squared. Now you have to note something here on the side, that the change in time will be defined by the change in time of b minus 1. Now this minus 1 is the 1 seconds here. Remember they said that ball 1 second after ball A is dropped, we actually thrown upwards. We actually throw ball B vertically upwards. So that means that the time that ball B is thrown is delayed by 1 second. Because remember, when ball A is somewhere here, we start throwing ball B. So it means on this time that it will take for ball B to go down, or any time that you define when as it goes down, we are going to subtract 1 second because it's delayed by 1 second. That's what I'm doing here. I'm saying the time that it takes for ball B to go down is delayed by 1 second. We subtract 1 second at every point as it goes down. Now, at this stage, it means I can substitute all the information that I have. My initial velocity here is going to be 9 meters per second because it really goes down with 9 meters per second. And we are saying here that the time of B is defined by I need to write this correctly. So here we're saying the time of B is actually defined by a change in t minus 1. Right, so here we're going to have the change in t minus 1 plus 1 over 2. Then here we have negative 9.8. Then here we have change in t minus 1 all squared. Now from here, we basically are simplifying. It becomes an algebraic equation that we need to simplify. So this means here I'm going to have the negative 9 change in t plus 9, because I'm multiplying this with that to get that, and I'm multiplying that to get a positive 9 there. The 1 over 2 times negative 9 would give me a negative 4.9, and here in the brackets I'm going to expand this, and we know that to expand this type of a binomial we're going to say t squared. So basically we're squaring the t, then we're taking these 2, we're multiplying it with change in t, we're multiplying it with 1. So I'm saying 2 times change in t times negative 1, and this should give me 2 change in t, because you know the 1 there would just give me that number. So I'm going to have a negative 2 change in t, and then we square the negative 1, which is going to be a plus 1. Now the next step here would be to remove the brackets there. So I'm still going to have this part being the same, and then I'm going to say 4.9 times the change in t squared, and I'm going to say this times that as well, which is going to give me a positive. If we multiply 4.9 by 2, we're going backwards. Remember, this was a half of that. So we're going back to 9.8 here. You can use your calculator really if you like, but this should be clear to you. Then if you multiply negative 4.9 by the 1 there, it gives me a negative 4.9. Now this means now I can group my like terms to get the height or position of the displacement of ball B at any time by grouping the like terms here. It should be clear that we only have one square here, so I'm going to start by putting this 4.9 changing t squared, because I want this to be in a standard form of a quadratic equation. So the second thing that I'm going to do is look at the 9 minus 9.8. I can see the 9 and the 9 will fall out. I'm going to be left with 0.9. So that means here I'm going to have not 0.9 but 0.8 change in t. You can use the calculator really, because I'm just subtracting the 9 here. I'm going to be left with 0.8. And 9.8 is bigger than 9. So it should be positive answer there. And then we are saying here that we look at the numbers now. The 9 minus the 4.9. Okay, that one I can use a calculator. 9 minus 4.9. 9 minus 4.9. And that actually gives me a positive 4.1. Again, this becomes an equation that defines the height at every time of the motion of the ball, right? It's a function of time as well. The displacement here is a function of time. I am going to call this first equation here equation 1, and call here this second equation equation 2. Likewise, remember that second equation gives us the height of this ball as it goes down, to say what height is it as the time changes, what height does it occupy, or displacement does it occupy as the time changes. Now, you will realize that I've explained that when this ball is somewhere at this point, ball B, this is 1 second later, right? Ball B will be dropped here. Well, not dropped, but will be thrown at 9 meters per second. Now, that means when this ball gets somewhere here, this one would be somewhere here. And when this gets to the maximum height, this one would be somewhere here. And as it comes back down, this one would be somewhere here. And as it goes down, this one will be somewhere here. You can see that at some point, as they go down, there will be a point where they actually have the same height here. They will catch up and be at the same height. And so that's the height that we're looking for, to say what is this height here of these balls. Well, particularly looking at ball A, which is the same height really. But what height will ball A have when these balls are at the same height from the ground? So that means we are looking at this height here, to say what is the height of these balls here. What is the height of ball A there? Now, you would realize here that perhaps if I use a different pen here, you realize that ball A would have been displaced, or would have occupied that displacement that goes in that direction. That means the change in Y of A would be displacement in that direction, and this would be a negative displacement because it goes in the negative direction. It goes downwards. Remember, we said down is negative. And actually, when you look at ball A from here to here, it will actually be displaced in that direction. This will be the displacement of A, and it will be a positive direction because actually it will be up. Now, this is to say that at this stage, a technique that I'm going to use is that if I take this height, so this is B, not A. If I take these two heights, if I say this height plus this height, I should get a total height here of the building, so the 30 here. Now, when we look at this in terms of our equations, what we're really saying is that if we take equation 1 and equation 2 and we add them up, if I say equation 1 plus equation 2, I'm saying I should get a height of 30 meters per second. 30 meters, meaning the height of the building. Remember that equation 1 and equation 2 represents the height at any time. So in this specific instance, we're looking at the height when the balls are at this point, are at this time. And when we add these two heights at that time, we should get that 30. Now, this means that I'm basically taking this equation 1 and I'm adding it to equation 2. Now, to do that, I'm literally going to take these two heights that I've defined. The height of equation 1, which is going to be A here, it is going to be the change in A, and then we have a plus here. And then the height of equation 2, which equation 2 is defined by B, is a negative because it goes down. So that means you're going to have a negative change in B, and this would be equals to 30. Now, from here, this becomes a matter of substituting these heights in terms of their equations. So I'm going to substitute this and that. So for the delta YA, we are really going to have 16 change in t minus 4.9 change in t, right? And for the delta yb, we are actually going to have well, firstly, maybe I can look at this. The positive and the negative will give me a negative. And when I put this, I'm going to have a negative 4.9 change in t squared is this now, right? And we're going to have plus 0.8 change in t plus 4.1. And we're saying this is equals to 30. Now, from here, this question really becomes very, very, very boring because it becomes a simple simplification problem. We are going to firstly start by removing the brackets here. So we're going to have a 16 minus 4.9 change in t. Here I'm going to have a plus 4.9 change in t, negative 0.8 change in t, negative 4.1. And this is equals to the 30. I'm just multiplying the negative here inside the brackets. That's why those numbers are changing from positive, negative, negative. Now at this stage, you can clearly see that the 4.9 squared. So here I didn't substitute this properly. This is a square here. We have a square here. We also have a square here. Remember, this is a squared, right? So these two would cancel each other out because they're exactly additive inverses of each other. And then now, when we look at the time here, the other like terms here is going to be the 16 minus the 0.8, which gives me the 15.2 change in t. So this is done, and I'm only have one number here, which is a like term to that. I'm going to take this to this side so that I have a 30 plus 4.1, right? We're going to have a 30 here plus 4.1 because this will be positive as it goes that side. So 30 plus 4.1, that should give me 34.1. And this means that our time would then be equal to, remember, I'm going to divide both sides by 15 so that I have 34.1 divided by 15.2. And this gives me a time of 2.24 seconds. Now remember, we're not calculating time here. We actually want the height. So what we have found here is the time at which these balls will be at the same height, is the time when they're at this height. That means I can then use that time in any of these two equations to find the height. Well, particularly in this case, the height of A, because we want the height of A. We don't want the height of B. So very important, we're going to use equation 1 here. So that means I'm going to say from equation 1, we are going to have the height of ball A to be defined as 16 times change in t minus 4.9 change in t squared. This is just equation 1. I'm taking equation 1. And at this stage, I'm just going to substitute the time at which the ball will be at this height. And that should give me that height, because remember, we said this formula assists us to get the height at any time. You know, we're getting the height at any time. So our time here, when the two balls are at the same height above the ground, would be given by 16 times the 2.24 minus 4.9. And here we have 2.24 that squared. And when we punch this on a calculator, we come up with an answer that would be given by 11.25 meters. So that means that the height at which ball A will be when the two balls they pass each other, when they start passing each other, this one going down and that going down, would actually be, this height there will be actually defined by 11.25. Now, the one thing that you may want to do is to navigate this answer to see that it makes sense. Obviously, this answer should be below the maximum height of ball A, because we figured that it will be somewhere when it comes down, because remember the time of 2.2 seconds would be after you have passed the maximum height. Remember, on our graphs you can clearly see that our maximum height occurs actually at 1.64, so 2.24 would be something here as we're approaching that 3, so it's somewhere when we are going down there. And we can see that that height is far below even where we started with 30. So that assures us that we are in the right direction. Now this question is marked out of 6, and what basically they're going to put attention on is the fact that you use the correct equation there and you set up equation 1. They'll also give you a mark for putting these correct substitutions here. Remember, you have to play around with time here and other variables, and also 1 mark for the fact that you set up the second equation there. So that's 4 marks at this stage, and the other mark will really come from being able to find the time, right? And that is 5 marks, and then the last mark will be finding the final answer.